Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you're looking for the most efficient shortcut to being fully informed on the cutting edge of science, you are in the right place. We take the source material, a breaking study, a massive data dump, and we distill it down into the core, fascinating insights you need.
And today we are undertaking a bit of a cosmic exploration. We're looking at a world that has, for decades really, represented our greatest hope for finding life beyond Earth, at least in our own solar system.
We're talking about Jupiter's spectacular ice-covered moon, Europa.
Exactly.
Europa is, it's an absolute magnet for speculation, and for really good reason. Jupiter, the gas giant, it shepherds nearly 100 moons. It's an astronomical number, truly.
It is a whole solar system in itself.
But Europa just stands out completely. The consensus among planetary scientists is that it harbors this vast global ocean of liquid salt water, and it's completely hidden beneath an icy exterior.
It's a true water world, and it's isolated from the sun's energy, which makes it, well, the ultimate enigma.
It is the ultimate enigma, yeah. But that potential for life, for habitability, it's always hinged on one single critical question. It's not simply, does Europa have water? Because, we're highly confident that it does.
Oh, absolutely. The evidence for the ocean is very strong. The real question, the one that matters, is does it have the dynamic energy that life needs to actually arise and, sustain itself within that water?
And that distinction, that is the absolute core of our analysis today.
Yeah.
The difference between just having the liquid, the solvent, and having the active chemical engine.
Right.
We are pulling insights from a brand new peer-reviewed study. It was just published in the journal Nature Communications. This research, it was led by Paul Byrne at Washington University in St. Louis, and they looked past the water itself. They focused intensely on the geology of the seafloor.
And their findings are, well, they're significant. They suggest we might need to radically recalibrate our expectations about Europa. The team used physics and some really detailed geological modeling to pour what you might call cold water, pardon the stellar pun.
Yeah, I was waiting for that one.
On the long-held excitement about Europa's potential to support life, at least life on its ocean floor.
Okay, let's unpack this. What this new study is suggesting is that the bottom of that vast ocean, maybe 100 kilometers deep, is geologically silent.
Silent, static, inert.
And that silence, if the modeling holds true, that is a catastrophic problem for any life that relies on chemical energy.
It's a huge problem, and the credibility of this work it's very high. This isn't just speculation. It's published in a top-tier journal, and it's grounded in meticulous calculations. They're combining known physical facts about Europa.
Its density, its size, how it orbits Jupiter.
All of that. And they combine it with detailed inferences drawn from how small rocky bodies behave, including Earth and our own moon. The team, Byrne and his colleagues, they focused all their energy on that often overlooked part of the puzzle, the seafloor.
And this is exactly where we need to start. We are diving down, past the ice, past the ocean, right to the bottom. So let's establish the scale of this place for you, the listener. Let's call this first part, the anatomy of a water world.
It really helps to visualize it first. Europa, it's actually, it's quite modest in size, a little bit smaller in diameter than our own moon.
Right, so you'd think smaller world, less stuff.
You would, but that scale is completely deceptive because its structure, how it's built, gives it this disproportionate, just immense volume of water.
It really is staggering. I read that if you could somehow gather all the liquid water on Earth, all our oceans, lakes, rivers, ice caps, everything. Europa is modeled to hold more water than all of it combined. And the moon itself is just a fraction of Earth's mass. That just blows my mind.
It's why the volume is so immense, and it's why this little moon has always held such promise. That volume is organized into three distinct layers.
Okay, so let's start at the top.
First, you have the ceiling, the ice shell. Current estimates, they put that shield of ice at somewhere between 15 and 25 kilometers thick.
15 to 25 kilometers. That is a colossal barrier between the surface and anything below it.
An incredible barrier. Then, beneath that shield, lies the ocean itself. And it's not some shallow sea. We're talking about a depth of up to 100 kilometers.
100 kilometers deep. I mean, just for perspective, that's 10 times deeper than the Marianas Trench, which is the deepest point we have here on Earth.
Precisely. It covers the entire moon. And then finally, beneath that immense volume of salty liquid water, that's where you find the third layer. A rocky core. It's analogous to the silicate rock mantle and core of Earth.
So you have the fundamental building blocks. You have liquid water and you have rock.
The two main ingredients.
But as you pointed out earlier, having water and rock is, what, 2/3 of the equation? You need energy. So what makes that rock-water interface, that seafloor, so absolutely essential for life in this dark, sunless environment?
Yeah, this is key. We have to completely move past the Earth-based idea of photosynthesis. I mean, in a cold, dark, deep-sea environment like that, life can't rely on the sun. There is no sun. So instead, it has to rely on chemical energy. It's a process we call chemototrophy.
And we have examples of this on Earth. You have to think about those incredible, almost alien-looking deep-sea ecosystems we've discovered. The ones clustered miles beneath the surface, completely cut off from the light.
Exactly.
We're talking about those giant tube worms, the colossal clams, all those specialized microbial mats living in total darkness.
And those organisms, they're not living off the sun. They're living off Earth's internal geological engine. That engine, it's driven by tectonic motion and volcanic activity, and it manifests as hydrothermal vents.
Or black smokers.
The black smokers, yeah. What happens is cold ocean water seeps down into the crust, it encounters these superheated magma chambers, and it gets chemically altered. It's cooked.
So it picks up all sorts of minerals and compounds.
It does. And that water then shoots back out through these vents at extremely high temperatures, carrying this rich chemical soup with it.
And it's that superheated plume, that chemical disequilibrium, that is the literal catalyst for life.
That's the perfect word for it, catalyst. The water coming out of those vents is rich in compounds like hydrogen sulfide, iron sulfides, methane, manganese, all these things that microbes can, well, eat.
They can metabolize it.
They metabolize it. These compounds, especially hydrogen sulfide, provide the energy needed to kickstart and sustain microbial life at the absolute base of the food chain. The microbes consume those chemicals, and then everything else in that ecosystem consumes the microbes.
So without that active geology, without that mechanism for energy cycling and chemical injection,
then even 100-kilometer deep ocean becomes a vast, cold, inert volume. It's just water and rock with no spark.
This is where that Burns study just hits so hard. They looked at the Earth analogy, and they calculated the odds of Europa providing those vents. And Byrne was very clear when he presented his team's conclusion. He said, and this really drives the point home, if we could explore that ocean with a remote-control submarine, we predict we wouldn't see any new fractures, active volcanoes, or plumes of hot water on the seafloor.
And the implication of that statement is immediate, and it's profound. If the seafloor is quiet, just like the models suggest, then there's no mechanism for cycling necessary nutrients from the rocky core up into the water.
And no way to provide that vital thermal energy.
None. The energy required to sustain a deep-sea chemoautotrophic ecosystem just isn't there. The lack of geologic activity at that vital rock-water boundary, it essentially means the available energy is negligible. The ocean floor might as well be a geologically dead zone.
But wait, I have to stop you on that point before we pivot to the calculation itself. Is it possible that just the fact that there is a rock-water interface and that the water is salty, is that enough to produce some chemistry, even without the big dramatic vents?
That's a crucial question.
Couldn't simple rock dissolution or, reactions between the salt and the silicates produce some energy? Even a little bit.
It's a crucial point, and it moves us into a realm of, let's call it, lower energy life support. And yes, it's possible, but the challenge there is immense. Simple water-rock reactions, they happen everywhere, but they are incredibly slow.
Diffuse.
Very diffuse, and they don't release a lot of energy. Hydrothermal vents, on the other hand, driven by active tectonics and volcanism, they create an intense, localized disequilibrium. A sudden, dramatic injection of heat and chemicals, that's what allows life to thrive rapidly.
Concentrated source.
Exactly. The Burns study is primarily arguing that Europa lacks that powerful engine, the one that creates these high-energy oases. So without that strong geological motor, any chemistry that does occur would be spread so thin, so slowly, that it might not be enough to initiate or sustain a thriving ecosystem.
That makes perfect sense. We're not just looking for a low-energy trickle here. We're looking for the powerhouse, the thing that creates a concentrated biological starting point.
Right.
So the big question is, how do they reach this quiet conclusion? This brings us to the scientific heart of the study, which is the physics and the calculation itself. So let's talk about it. Where did the heat go?
Absolutely. The researchers, they relied on some really fundamental planetary physics and gravitational modeling. They had to figure out whether Europa possesses enough internal heat to cause that significant motion required for, say, plate tectonics or volcanism at the seafloor.
And they looked at two main heat sources, right?
Two main sources, yes. The first is the internal furnace, residual heat, the heat left over from when the moon first formed.
Okay, so source number one. Why is Earth's core still blazing hot billions of years later, yet Europa's core is predicted to be, thermally inert?
It's a classic example of how scale, just sheer size, affects how a planet cools over cosmic time. Imagine you have a small cup of hot coffee versus a massive insulated urn of coffee.
Okay, I'm with you.
They both start out hot, but the small cup, because it has a low mass to surface area ratio, it loses its heat very, very quickly to the surrounding air.
Right, it cools down in minutes. And Earth is the massive urn, holding onto its heat much more efficiently.
Precisely. Earth is large enough, it's massive enough, that it retains heat not just from its primordial formation, but also from the ongoing decay of radioactive isotopes within its mantle, things like uranium and thorium.
So that radioactive decay acts like a long-term, slow-burning internal heating element.
Exactly. It's what sustains the convection in our mantle and drives plate tectonics over billions of years. It keeps the engine running.
But Europa being comparable in size to our own moon, it's the small cup of coffee.
Correct. Europa simply lacks the thermal mass to hold on to that primordial heat for very long. The sheer volume of rock and the insulation effect are just so much smaller. Byrne and his team, they calculated that any heat that was originally present in Europa's rocky core, it would have entirely dissipated into space.
Radiating away through the crust and the ocean.
Billions of years ago. So by the time we observe Europa today, that internal furnace is predicted to be cold. Thermally speaking, of course.
So we can scratch off residual planetary heat that's not driving any contemporary seafloor activity. The core is cold. That means the only viable engine left for keeping the geology dynamic must come from the outside.
From Jupiter itself.
From Jupiter.
And this is where we move into the incredibly dynamic and very powerful realm of tidal heating. This is a kinetic energy source. It's the mechanical flexing and friction that's generated by Jupiter's immense gravity. And that force is strong enough to keep a moon geologically alive, even without any residual internal heat.
Here's where the physics gets incredibly powerful, and really where the difference between life and no life just hangs in the balance. We have to compare Europa to its incredibly volatile sibling, AOO.
The tale of two moons.
Exactly.
The Io-Europa contrast is, it's the perfect teaching moment in planetary science. Io is, quite literally, the most volcanically active body we know of in the entire solar system. Its surface is just constantly being repaved by spectacular eruptions.
And that phenomenal activity is 100% driven by tidal heating.
100%. But it's not just from Jupiter's simple gravity. It's driven by the asymmetry of that gravity, the unevenness of the pull.
Okay, so explain that asymmetry for us. What makes Io's orbit so special and so heating?
So Io is the innermost of Jupiter's 4 large Galilean moons. And crucially, its orbit is not a perfect circle. We describe it as eccentric or erratic.
And why is that? Why hasn't it settled down?
Well, this eccentricity is maintained by a complex gravitational dance, a resonance, with Europa and Ganymede, its two outer neighbors. As these moons pass each other in their orbits, they give Io a periodic gravitational tug. A little nudge.
And that little tug is enough to prevent Io from settling into a nice, stable circular path. It keeps it wobbly.
Exactly. Because its orbit is elliptical or oval-shaped, Io is constantly moving a little closer to Jupiter and then a little further away. And when it's close to that gas giant, the gravitational pull is extreme. When it's further away, the pull relaxes a bit. This constant, differential, and uneven tugging, it subjects Io to intense cyclical stress.
It's like taking a rigid stress ball and just continuously squeezing and relaxing it thousands and thousands of times a year. The friction generated inside must be immense.
That's a perfect analogy. The immense constant friction generated by this physical deformation, this tidal flexing, is what converts kinetic energy into thermal energy. It roils the rocks beneath Io's crust so intensely that the moon's interior is largely molten.
Which is what drives those massive, non-stop volcanic eruptions that spew out sulfur and silicate lava.
Io is truly alive because of Jupiter's intense asymmetrical gravitational pull and its own unstable orbit.
Okay, so now let's turn to Europa. This is where the burn study focused its most powerful calculations. What happens when you apply that same physics to Europa's position and its orbit?
Well, Europa's story is fundamentally different, while it is also tidally heated. I mean, if it weren't, the ocean wouldn't be liquid in the first place.
Right, that's a key point. There is some heating.
There is some heating, absolutely. But its orbital parameters are just far more moderate. For one, Europa is further away from Jupiter than Io is, and critically, its orbit is significantly more stable and more circular.
So the stability that makes Europa's journey predictable is, paradoxically, the very thing that keeps its internal geological engine from running hot.
That's the key finding of the study. The gravitational tug on Europa is much gentler, and it's much more symmetrical than it is on Io. This gentler pull does cause flexing, but the crucial differentiation that the burn team made is related to the magnitude of that flexing on different parts of the moon.
Okay, we need to nail this distinction down for the listener. What part of Europa is getting heated and what part is staying cold?
So the calculations suggest that the tidal forces are strong enough to cause significant movement and friction within the outer ice shell.
The sealing.
The sealing, yes. This is why we believe the ice shell is dynamic. It cracks, it refreezes, it might have plumes shooting out. This flexing in the ice is what generates enough heat to melt the water below the ice, and that's what maintains that 100-kilometer deep liquid ocean.
So that's the easy part of the equation. The heat keeps the ocean liquid.
That's the easy part. The tough part is the rocky core, which is sitting 100 kilometers beneath the ocean.
The rock-water boundary.
Exactly. The calculation suggests that the energy required to melt a 15 to 25-kilometer ice shell is vastly, vastly less than the energy required to induce tectonic plate motion and volcanic activity in a massive, dense, rocky core.
It's just a different physical problem.
A completely different problem. Europa's orbital stability means the differential stress, the squeezing that's applied to the deep rocky core, is minimal. There just isn't enough friction being generated at that depth to sustain the high temperatures or the convection currents that you would need to drive seafloor geology.
So in essence, the heat generated by Jupiter's pull is localized. It's concentrated in the elastic layers, the ice, and the liquid water, and it just dissipates before it can effectively fire up the planet's deep internal systems.
Right. The core remains cold and inert.
That is the precise verdict on tidal heating.
It is. The forces today are simply not strong enough to drive any sort of significant active geologic activity at that rock-water boundary. The energy budget for geological activity is just insufficient. As Byrne noted, we don't see any volcanoes shooting out of the ice today like we see on Io, and that's because the engine required to produce those intense geological events is, for all intents and purposes, switched off.
That is a staggering conclusion, and it's drawn purely from physics. So we've established that the residual heat from formation is long gone, and the current dynamic heat source, tidal flexing, is too gentle to reach the core. This leads us perfectly into the big so what. If the physics tell us the seafloor is cold and silent, what does a geologically quiet ocean actually mean for life? This is where we analyze the implications.
And this is where we synthesize the findings and apply them directly to that core question of habitability. The conclusion from the Nature Communications study is stark. Europa likely lacks tectonic motion, it lacks warm hydrothermal vents, and therefore it lacks the robust cycling mechanisms that are required to create and sustain a vibrant ecosystem.
It's a vast, dark, cold world at the bottom, despite the incredible volume of water that's sitting above it.
And if the seafloor is inert, that essential link that's required to support deep-sea life is broken. Let's just reiterate why that cycling mechanism is so critical. On Earth, the deep ocean is, for the most part, a chemical desert.
Right, there's not much going on.
Not much at all, except where geological forces provide a massive, concentrated influx of nutrients and energy from below.
So if Europa lacks those vents, what are the remaining sources of chemistry available to that 100-kilometer deep ocean? I mean, we have to consider every single possibility, no matter how remote.
We essentially have two possibilities left, and both of them are what I'd call low-energy options compared to hydrothermal vents. The first is, as you mentioned earlier, that slow water-rock interaction.
The trickling background chemistry.
Which is very diffuse and likely way too slow to support a concentrated food web. And the second possible source must come from the top, from the ice itself.
Okay, what do you mean?
The surface of Europa is constantly being zapped by Jupiter's intense radiation field. The moon is sitting inside these powerful radiation belts, and this bombardment of energetic particles, it breaks up water molecules on the surface, and it creates other compounds.
That's good, right.
Exactly. Things like oxygen, hydrogen peroxide, and various sulfur compounds. So you have all these chemical oxidants sitting right there on the surface, essentially frozen into the ice shell.
I see. So the theory is that if the ice shell is dynamic, if there are cracks, or if the ice melts and refreezes, a process called convection,
then these oxidants might eventually be mixed or transported down into the deep liquid ocean below. And this process, if it happens efficiently, could provide a different kind of chemical energy source for life. It could allow organisms to metabolize the compounds that are supplied from the surface.
But the challenge there, I mean, it seems immense, too. You're talking about transporting surface chemicals through a 20-kilometer thick shield of solid ice, and then through 100 kilometers of water, just to get them to the rocky core where life might have begun.
It's an issue of supply chain efficiency.
That's a great way to put it.
Hydrothermal vents deliver high-energy nutrients directly and consistently right at the life rock boundary. It's like having a supermarket at your front door. The surface-imported chemistry is a slow, complex, and potentially intermittent delivery system. It relies entirely on the dynamics of the ice shell, which, frankly, we still do not fully understand.
So the Burns study, by reeling out the high-energy guaranteed source, the seafloor vents, it makes the whole life scenario immediately more challenging.
Much more challenging. And it forces the scientific community and you, the listener, to confront a very important distinction that I think we've glossed over for years. We've sort of been conditioned to think that finding liquid water automatically equals high habitability potential.
To follow the water mantra.
And the source material really challenges that simplicity head on. Just having liquid water, even in abundance, is not enough. You have to have sustained dynamic energy input at the most critical chemical interface, the water-rock boundary. The ocean might be warm enough to be liquid, but the seafloor itself is predicted to be cold, inert, and featureless, offering little to no concentrated energy to initiate a food web.
I have to challenge this conclusion slightly, though. The model predicts a lack of contemporary activity right now. But we've seen microbes on Earth, we call them extremophiles, that can survive incredible periods of stasis. They can thrive in extremely low-energy environments.
True.
So if life did arise on Europa billions of years ago, when the moon may have had much more heating, couldn't a simpler form of life have adapted to survive in these low-energy conditions today?
That's a highly relevant query. It's a great point, because we do see life adapting to what we would consider marginal conditions. However, we have to differentiate between sustaining life under marginal conditions and starting life.
Oh, okay, abiogenesis.
Abiogenesis, the origin of life. That process seems to require a highly dynamic, energetic, and chemically diverse environment. Something like the ones we hypothesize existed near early Earth's hydrothermal vents. The chemical complexity that you need to build the first self-replicating molecules is immense. You need a lot of stuff happening in one place.
So you're saying the startup energy is much higher than the maintenance energy?
Precisely. If Europa's seafloor was intensely heated billions of years ago, maybe when the moon had a more eccentric, a more wobbly orbit, then life could theoretically have started. But as that orbit stabilized and the core's heat dissipated, any thriving ecosystem would have been starved of its primary food source.
The geological buffet would have closed down.
It would have. And any surviving organisms would have needed to switch from a high-energy metabolic process to an incredibly slow, low-energy one, maybe consuming those diffuse background chemicals or relying on those slowly imported oxidants from the surface.
So in that scenario, we're not looking for a vibrant deep-sea oasis. We're looking for, what, a microbial ghost town? Organisms that maybe reproduce once every million years?
It completely changes the search. We go from looking for a bustling city to looking for a deep freeze survival bunker. The implications of the Burns study suggest that even if life is present on Europa today, it would be incredibly sparse, very difficult to detect, and likely highly specialized to use the minimal energy available from slow rock-water interaction or those sparse surface-delivered oxidants.
It's a profoundly different scientific challenge than finding a planet driven by its own internal thermal engine.
Completely different. And that framing, I think, makes the findings much clearer. The absence of a strong geological motor doesn't completely rule out life, but it certainly argues strongly against the kind of robust, complex, deep-sea life we initially hoped for.
And it serves as a massive check on our enthusiasm. It reminds us that the physical mechanisms governing habitability are incredibly sensitive to astronomical mechanics, like orbital resonance and planetary scale.
It all comes back to physics.
So if the calculations are right, the search for robust contemporary life just got a lot harder. But as scientists, we never accept a calculation, no matter how elegant it is the final word. We need direct observation.
Always.
And this moves us perfectly to our final segment, discussing the path to certainty and the spirit of exploration.
That's the absolute imperative of science. The study is a prediction. It's a very strong one based on established physics, but it is not a direct observation of the conditions 100 kilometers below the ice. The only path to challenging or confirming this data is through a physical mission.
And the key mission that's set to provide that certainty is already underway, the Europa Clipper spacecraft.
The Clipper mission is it's designed specifically to investigate Europa's potential habitability. It will perform dozens of close-up flybys, it'll circle Jupiter, and then skim past Europa again and again to gather massive amounts of data. It's an incredibly ambitious mission with instrumentation designed to probe the very layers we've been discussing.
So what specifically will Clipper be measuring that will help us verify or, refute the Byrne team's conclusions about the core?
Clipper will provide crucial measurements that feed directly back into these models. For instance, it's going to use radar to penetrate the ice and measure its precise thickness and structure. And it will use gravity and magnetic field measurements to determine the depth and salinity of the ocean, and importantly, the dynamic flexing of the ocean and the core.
So if the core is being subjected to tidal forces strong enough to induce tectonics, the gravitational field measurements would likely show some kind of subtle but measurable signature related to that movement.
Exactly. The instrumentation will be precise enough to measure the physical deformation, how much the entire moon flexes under Jupiter's pull. If the moon is flexing significantly across its rocky interior, that indicates immense internal friction and heat, which would immediately contradict the Byrne model.
And if, however, the flexing is largely confined to the water and the ice layers,
then the Byrne model stands validated.
When can we expect this crucial data to start rolling in and hopefully answering these questions?
Well, Clipper is scheduled for its deep investigation, starting with its first flyby in the spring of 2031, so we have a little while to wait.
It's a patient pursuit.
It is. But the level of detail we will gain after a few dozen flybys will far, far exceed anything we have today.
It's also worth pausing just to acknowledge the human story behind this mission. The Clipper was conceived and championed in part by figures like Bill McKinnon, the Clarkway Harrison Distinguished Professor at Washington University. It just highlights the decades of relentless curiosity that propel planetary science forward. This is a scientific effort that really spans generations.
And that institutional knowledge, the kind that allows researchers like Byrne and his team to refine these models over time, is fundamental. It's what helps reduce the risks of major space missions. Every piece of data, whether it's confirming a planet's density or refining its orbital eccentricity, it allows us to build a more accurate picture before we commit billions of dollars to the trip.
But I want to return to something Paul Byrne said, because I think it speaks to the greater spirit of exploration that goes beyond just the search for life. He isn't solely focused on the life question. His curiosity is fundamentally geological.
He shifts the focus so beautifully. Even if Clipper confirms the seafloor is dead and inert, even if modern Europa is found to be lifeless, Byrne is still incredibly interested in the fundamental science. His primary geological question is simply, I'm really interested to know what that seafloor looks like.
That is profound. For all our discussions about the ocean and the ice, we have virtually no data on the ocean floor itself. It could be vast, flat plains of rock, or it could be littered with ancient, cold, dormant geological features. We just don't know.
It's the joy of pure discovery. The core motivation of a planetary scientist is to simply know what's out there, even if the answer doesn't fit our hopes for alien life. And Byrne's broader view is very grounding for all of us. He says he's not upset if they don't find life on this particular moon, noting he is confident that there is life out there somewhere, even if it's 100 light years away.
So the value of the mission, it isn't just a binary yes or no on life. It's about defining the parameters of habitability and understanding the complex, varied geology of the Jovian system. Every planet and moon is a lesson in how physical laws manifest differently based on size, composition, and location.
And the data gathered, regardless of the conclusion, will inform where we look next. If Europa, with its massive water ocean, turns out to be geologically inert because of its distant, stable orbit, well, that tells us that tidal heating is a highly sensitive variable in the habitability equation.
And we would then focus our search for high-energy ecosystems on moons with more eccentric, unstable orbits closer to their parent planets.
Exactly. Every discovery, even a negative one, refines the search.
This analysis has truly clarified the complexity of the physics at play here.
Indeed. We've taken a really detailed look into the latest thinking on Jupiter's prime candidate for life, Europa, based on the rigorous physics presented in that Nature Communications study.
So what does this all mean for you, the listener? Let's review the central insight. While Europa has the liquid water, that first critical ingredient, the latest calculations show that the lack of dynamic tidal heating at the seafloor, which is driven by its distant and stable orbit around Jupiter, likely means the ocean floor is geologically quiet.
And that quietness starves the ocean of the chemical and thermal energy that's needed for a thriving contemporary ecosystem. It's the difference between having a gigantic insulated pool of water and having a vibrant, geochemically active hydrothermal ecosystem.
And Europa might just be the former.
The life potential is, well, it's significantly lower than we previously assumed. It shifts our focus to lower energy possibilities or even just historical possibilities.
Now, for a final provocative thought to mull over, one that builds directly on the source material. We noted that the study focuses on contemporary life right now, and it acknowledges the moon may have had a lot more heating in the distant past.
So, if the Europa Clipper arrives in 2031 and confirms a static, inert environment today, the search doesn't end, it just pivots to history. We would then need to ask, if life did arise when the heating was more intense billions of years ago, and then starved when the orbit stabilized and the core cooled, where would we look for the evidence?
For fossilized or long-dormant microbial evidence.
Exactly. That is a fundamental change in mission. If life started when the heat was on, and then the stability of Jupiter's orbit led to geological silence, how would those ancient organisms have fared? Would they have simply been encased in rock, frozen into the cold seafloor, awaiting a geological revival that never came?
That's a whole new type of exploration.
It is. That historical investigation requires us to think about how to search for ancient biosignatures, the chemical traces of life, rather than active metabolisms. It means future missions would need specialized drills and analysis tools designed to penetrate the seafloor rock, not just sample the water. It reminds us that habitability isn't a permanent switch. It's a continuum that can flicker on and off over geological timescales, and we may simply be arriving billions of years too late for the show.
A truly fascinating and, I think, an essential recalibration of our expectations. We started this looking for an active ecosystem, and we've ended by contemplating a frozen, fossilized past. Thank you for walking us through the complex physics governing Europa's silent seafloor.